Hello, my name is Andres Cordova and my teammate is Celeste Domeno, and this is our presentation number 2 for the class Engineering 460. What it means to evaluate an integral. When referring to an integral, the evaluation of the integral is basically to test the value of the integral in order to determine the accuracy of it. This process can be done with several methods. What is the integral being evaluated? An integral can be evaluated by many methods. Among them we found the analytic methods, simulations, and geometric method. It's basically the area below the curve. As we can see from this picture, here we have a curve defined by a function, and the integral of this function with bounds in a and b, well, a lower bound in a and an upper bound in b, can be defined by the area below the curve of the function f of x. So are we looking for the area of the integral? As I stated before, the value of an integral can be defined as the area below the defined function curve. So basically, as I said before, the integral is the area below a function curve. What it means to evaluate an integral? Can we just do the integration? No, because in real life problems, we will find some functions that are not going to be easily replicable or are impossible to be solved by analytical or conventional methods. That is why simulation is a helpful tool to determine the approximate value of some functions. So basically here, we're stating the fact that no, the integration is not always possible because, for example, when we're talking about distributions, we cannot simply integrate the integral in order to get a good value. But what we can do is we can get a good result by doing some simulations. So why are we even considering a simulation of data points to find the area? The simulation of data points to find a specific area is the best approach to solve complicated mathematical problems. When replacing the average of the value of n random uniform numbers in the expected function, we can get a pretty close result to the real value of the function. And the only way to solve this is with Monte Carlo. So using Monte Carlo, we can get a pretty close result. It's like a estimation of the result of the real value. So the concept of expectation. The expectation or expected value of a random variable is the average of all the possible outcomes from it. For example, the expected value of rolling a 6-sided dice is 3.5, because the average of all of the numbers that come up in an extremely large number of rolls is close to 3.5. So what does it mean? So basically it means that in this example I have a dice with 6 sides. So my possible outcomes are 1, 2, 3, 4, 5, and 6. So what will be the expected value of the dice? The expected value of the die will be the average of all these possible numbers, which will be equal to 3.5. So what is meant by Monte Carlo is an integral estimation. This statement, we can estimate the value of any integrand, no matter how complex the integrand, is important. Why? Yes, this statement is important because it references the importance of simulation as a means to solve problems that cannot be solved easily, or maybe it doesn't have an analytical solution. But with a simulation, we won't always find the right answer, although we can get a closer value to the optimal solution. So basically, Monte Carlo is used to approximate your value to the real answer or to the optimal answer. What relationships do integrations, probability densities, and fissionable materials have in common? Even though all of them have different complexity, we can predict or simulate their behavior through Monte Carlo.
Okay, so the complex distribution function that we are going to use is the Cauchy distribution, and then we're going to try and solve this in MATLAB using the function below, which is 1 over pi times 1 plus x squared. and we're going to solve this integral from negative infinity to 0. What we hope to obtain here is we have a graph of the actual Cauchy distribution, and then we're going to see if by using the histogram function in MATLAB we can plot something similar to this. So now we're going to go over to MATLAB, look at the code, and then solve it, and then hopefully we get something similar to this graph on the slide. Alright, so now over in MATLAB we're going to try and solve the Cauchy distribution here, and then this is the code for it. I'm just going to do a quick overview of how the code is going to run and what we're actually looking to have at the end of this. So first off, as you can see, we're going to run our sims x ra, and then we're going to solve that function in the previous slide as an integral on support from negative infinity to x. And then after we find I, we're going to put that into a and then solve for that for I equals 1 up to 1,000. Our r is going to be random, and then we hope that when we plot the histogram it'll be similar to the CDF that we have in the previous slide. So what I'm going to do, so we're going to go ahead and run this code, and then hopefully the histogram will resemble a Cauchy distribution. Okay, so first thing I notice here, I see a warning. Let's go ahead and read that. It says the solution is valid under the following conditions. Okay, so basically what this is saying that we need to include our return condition option to prevent this warning, but our code will still run. So let's go ahead and see what I is. So when we try and find I, see that I is the a tan x divided by pi plus 1 over 2. And then when we want to find a happens to be the tan of pi times r minus half. So I'm just going to go ahead and then plot this histogram again. See what we get. Okay, so as you can see, let's plot here. I'm going to maximize this to make it better. This histogram does resemble the histogram from the previous slide. Shows the peak all the way here and then the values all the way at the bottom. I maximized this so you can see that the values at the bottom are not necessarily zeros. They're just a little bit above the line, the 0 line. And this is an example of a complex distribution function.